Hi, my name is Christopher Moran. I'm a lead consultant for a technology firm in Sydney, Australia. Auric is the result of approximately a year's work. The plan was to create an autonomous rover platform which could deal with not only a variety of terrains, but also be able to navigate itself between 2 points, manage obstacles it finds along the way, and also follow a path without requiring special markings on the road. So not only could it follow a road or a footpath, but also a trail through bushland, for example. Auric is based on a 4-track tank-like frame which was salvaged from another project. Each of the track assemblies has a synthetic track and an independent motor gearbox assembly. We will control those motors individually through an intelligent motion controller, so there is redundancy in all the drive systems. Because Auric needs to be self-contained when it's operating, it has to be battery powered. The power in this case comes from a 7.2 volt lithium polymer pack, which is commonly found in large remote control vehicles. It's approximately 6.2 amp hours, 2600 milliamp hours if you prefer that discussion. That power goes to 2 places. Firstly, to the intelligent motion controller and also to a switch mode power supply. The purpose of the switch mode supply is to bring the 7.2 volts up to 12 so that we can feed the central controller. The intelligent motion controller will not only regulate that voltage to 5 volts for the logic supply, but it will also supply that raw input voltage to the motors via its onboard H-bridge controllers. The heart of the processing is a Friendly Electronics NanoPC T4 processor board. This uses a 5-core ARM CPU with 4 gigabytes of dynamic memory and 16 gigabytes of storage. This controller also features the usual things you would find in a small system: Ethernet, wireless, USB, video, SPI, GPIO and I2C. We use almost all of those functions throughout the development and operation of this machine, although we try not to use or rely on the video because the machine is designed to operate headless. The code that runs on that board was written from scratch in C++. It sits on top of a Ubuntu Linux 18.04 LTS distribution. There's no middleware such as ROS or similar in there. It talks natively to the operating system. I did this to get as close to the metal as I could, and this software has been developed over about the last 2 years and is developed really organically. There are a number of obvious subsystems which can be seen on the chassis itself. The first of these is the video camera, which is a Logitech C920S high definition camera, normally used for video conferencing applications. The blue structure at the top front is a YD LiDAR X4 manufactured by EAI. This is a very low cost LiDAR unit, really an entry-level device. It was intended for use in machines such as autonomous vacuum cleaners, but it suits our purpose quite nicely. It operates at a 400 Hz cycle rate and produces a 0 to 256 intensity value from which we can gather the proximity of any objects that we're passing by. Additional features include a GPS receiver, a compass based on a magnetometer device, so we can apply not only coordinate-based navigation to get from A to B, we can also use dead reckoning. The libraries within the core software which I developed can plot a course between 2 points, and it will rely on a combination of the magnetometer and GPS to ensure that it stays on track. I decided early in the design to split out the central processing from motor control and steering. This was done based on past experience where these compact microcomputer boards are not generally suited to real-time processing for motor control, steering and so on. I also found that the GPIO libraries that were designed to operate with the Nano PC did not handle PWM functions especially well. As a result, I created what I call an intelligent motion controller, which is based primarily on an Arduino Uno board to provide its processing and a dual H-bridge L298P motor controller. This controller can support 2 independent sets of motors, so we treat the motors on Auric on a per side basis, so that we drive both the front and rear motor on one side at the same time and in the same direction. It avoids us having to synchronize speeds between motors on one side, which would cause all sorts of drag and energy management problems. The communication between the central processor and the IMC is over 115,200 BPS serial link. There's a fairly simple command response protocol which I developed, and that can be easily extended to support new functions in the future. I was concerned that battery life would be a problem. I ran a life test on the unit running the motors under full load but stationary. We were able to run for more than 2 hours continuously. In the field, the chassis ran for over an hour and had only dropped to 85% of its capacity, so there's still plenty of room to work with there. It also means that I could probably carry a larger load of equipment, which would enable me to measure the environment around me much more accurately. I'm not quite sure what we'll find, but you never know.